considerable experience of having practiced some of these questions, but most often it's either a combustion at the top. If it's a combustion at the top, what do we do now? What do we do next? Well, we look at the data we've been given. And the data we've been given is almost always delta H formations for those substances. And the definition is there what a delta H formation is. So what do we do here?
You find delta H formation that the reactant inside the product.
What do I write in?
Elements.
Elements, yes. What I put down here is I write the elements in here. I just write my elements in here. And then all I do is I draw my arrows to show, right, I'm going to form this, and then I'm going to form this from my elements. Okay. Is everyone with me on this? Okay. So if you've got a combustion along the top and you're given formations, whenever if you're given values for delta H formation, you have to start with the elements. Now, do you know something? You can even just write elements. You don't even have to write them in. You can just write elements, because all you have to do is you have to say, right, well, I'm forming 1 mole of methane, so this is going to be to the value of 1 times delta H formation of methane. So I've written 1 times delta HF methane, and then formation of oxygen. Don't need it. Why?
Because it's diatomic.
No, because it's already an element, so it doesn't change. Because the element down here will be O2, won't it? And this is still O, and this is O2, so nothing changes. And here you'll have 1 mole of 1 times delta H formation of carbon dioxide, and this will be 2 times delta H formation of water. Okay, right? Then what you do is you say, okay, now I'm going to find from here to here. So you say your delta H of reaction is equal to, well, it has to be minus that, because if the energy change in that direction is, that's the delta H formation, that will be the energy change in that direction. So it's going to be minus delta HF of CH4, and then you're going with the arrow, so it's going to be plus delta HF of CO2 plus 2 times delta HF of H2O. Okay. Now, does everyone understand the principle there? Yes? Okay, so that's the first type. The second type you get is where you are given, say, a formation. Now, let's supposing you've got nitrogen plus hydrogen forming ammonia. And the question is, what's the delta H for that reaction? Delta H for that reaction. And you're given combustion values.
So what's delta H R?
Delta H reaction. Delta H reaction. Okay. So just delta H for this particular reaction. Okay. So again, you are asked to find delta H reaction. Well, if you're given combustion values, what do you put down here instead? This is if you're given. Sorry. So this is if you're given. If you're making notes, this is if you're given formation values. And the key thing is, if you're given formation values, you have to put the elements down here, and then the arrows have to go up. Okay. If you're given combustion values, what do you put down here, and where do the arrows go?
Combustion.
You put the products of combustion, and the arrows go down. So what will the products of complete combustion be here? Yeah, nitrogen dioxide and water, the products of complete combustion. Okay. And we would balance it up if you wanted to. You don't have to balance it up, because all you need to say is, look, there's 1 mole of this, so it's delta H combustion for 1 mole of nitrogen, delta H combustion for 3 moles of hydrogen, and then here, delta H combustion for 2 moles of ammonia. And once again, your delta H of reaction here will be equal to plus that value. So I'm just going to call that for now A and B. So it would be plus A, and then you're going to go back this way, so it's minus B. Because you have to invert the sign as you go round, because we're going from here to here. This is the reaction we're trying to find. Okay. And that's how you use Hess's law. Now, I'm afraid that sometimes the questions don't always fit that pattern. They often do. You're often given delta H formations or delta H combustions, in which case you use those techniques. But sometimes you're given something which is completely doesn't fit that pattern, and so you have to be creative, I'm afraid. But that will come with a bit of practice doing the questions. Kieran.
Why do you need to go via the combustion bit to go to NO2 plus H2O? Why do you need to take that route? Is there no formation?
Sorry, what do you mean? Is this
you're not given that.
That's what you're given.
No, the point is that I mean, if you if you had a book of data and one day you wanted to know what the delta H for this reaction was, you could just look up the delta H formation of ammonia. Yes.
Okay.
But remember, the delta H formation of ammonia will be for 1 mole of ammonia, and what I've written there is actually for 2 moles. So for that particular reaction, you'd have to double it. Yes. But I'm not saying that. I'm saying that in an exam, you're given that equation, and they say, and then they give you the combustion values for those 3 things: nitrogen, hydrogen, and ammonia, and they tell you to work out the equation, the value, okay? Because remember that you'll have a few multiple choice questions on Hess's law, and you won't have a data book. So you just have to work with what you're given. So they'll say, here's the reaction, here is some data, find out the delta H of this reaction, okay? Right, now, any questions about that? Now, there's one other thing as well that you need to just bear in mind. It's a bit like Hess's law, but in a way it's a little bit different, and that is bond energies. So, sometimes you can use bond energies to find the delta H for a reaction too, and you can say, okay, let's look at this same reaction here. That goes to carbon dioxide and to water, and we've got 2 molecules of water. So what we can do is we can actually say, right, let's calculate these. Let's calculate this delta H using bond energies. So again, what's our delta H? Well, all we have to do here is we say, well, if we look in our data book, we can find what these bond energies are. And we say, right, we've got 1, 2, 3, 4 carbon-hydrogen bonds that we're going to break. So 4 times carbon-hydrogen, that's the ones we're breaking. And then we're also breaking 2 times oxygen-oxygen double bonds. Okay, please don't talk unless you've got a question. And what we do is we find out those values and we add them up, and that's the energy that we require to break bonds. Breaking bonds is endothermic, isn't it? Do you remember? Breaking bonds is endothermic, so this will be a plus value. Okay. And then what we do is we say, right, what about the bonds which are made? Well, I've made 2 times carbon-oxygen double bonds, and I'm going to make 1, 2, 3, 4 hydrogen-oxygen single bonds. And what I do is I add those up, and that value is negative because making bonds is exothermic, and so that's going to be a negative value for my delta H. And so all you do is you then add those 2 together. Now, obviously, if the energy to break the bonds is greater than the energy of the bonds made, the value will end up positive, and delta H will be positive, endothermic, which is what you'd expect. If you have to put more energy to break the bonds than the energy you get out when bonds are made. But if it's the other way around, and you get more energy out when the bonds are made, then of course the negative will be bigger than the positive in magnitude, and therefore your delta H will end up negative, which is what you'd expect, because it's exothermic. Okay. Now if I do this, and this is an important point, they always ask this question, if this crops up and they give you bond energies and they say calculate the delta H, they always ask this question. They say, why is the delta H calculated incorrect? They always say, why is the delta H incorrect, or why doesn't it match this other value? So tell me now, what's the problem with doing this?
It's an average.
Good. Bond energies are, you need to know the definition of bond energies. And the first problem is that they are averages. They are averages across all different molecules. They're not specific to, in this case, methane or oxygen. Well, actually, oxygen-oxygen double bond is specific to oxygen. Because there's nothing else that has an oxygen-oxygen double bond. Apart from you, I suppose you could argue ozone, but that's so, but in general, they're not specific. They're not specific to these molecules, so they are averages. What's the other problem?
That fact that we take an average of the isotope. Is that
That's a good point. Yes, isotope does make a difference to bond energies because they're more massive, so the vibrations are different, so the bond energy is weaker. But you wouldn't be expected to say that. There's another key point though. You need to have. What's the definition of a bond energy?
energy required to break one?
Yeah.
The state.
The state.
Oh, right.
Gases.
Gaseous state. Right.
Yeah, we can.
So the bond energy is the energy required to break 1 mole of bonds in the gaseous state. You need to be able to write that because that's one of the definitions you need to know. So I'll say it again. The bond energy is the average energy required to break 1 mole of bonds in the gaseous